In the depths of the universe, there exist mysterious regions where even light cannot escape, and time and space are warped, dragged into the unknown. For over a century, we have carefully studied these enigmatic areas, yet we still haven't fully unraveled their secrets. These regions I'm referring to are none other than black holes. So, what lies inside a black hole? Or what happens if you fall into one? Could these mysterious formations be gateways to another universe? In this documentary, we attempt to understand black holes and explore various theories about them. But before that, let's examine who first noticed these mysterious regions and how they were discovered. The initial ideas about the existence of black holes actually date back much further than we might think. For example, in the 18th century, English physicist John Michel and French mathematician Pierre-Simon Laplace used gravitational theory to propose that there could be objects so dense that not even light could escape them. Michel, based on Newton's classical laws of gravity, calculated that if there were a star large and dense enough in the universe, even its own light could not escape it. However, this idea was seen merely as a theoretical speculation at the time. By the 20th century, black holes began to gain real recognition in the scientific world. This was made possible by Albert Einstein's development of the theory of general relativity in 1915. Although Einstein's equations showed how mass could warp space and time, they did not directly predict the existence of black holes. It was at this point that German physicist Karl Schwarzschild, using Einstein's equations, mathematically proved the possibility of a point where gravitational pull becomes infinitely dense. By 1967, John Wheeler advanced this idea and named these hypothetical mysterious structures black holes. Thus, the term black hole entered the scientific lexicon. From this point on, the most important question for scientists was, are there really formations in the universe from which nothing can escape? In other words, are black holes real? The answers to these questions were provided thanks to advancing technology. By the 1970s, astronomers began making X-ray observations and searching for black holes. Mathematical models suggested that these objects would have a gravitational pull so strong that they wouldn't emit light, but they could indirectly emit radiation. This radiation occurs due to the materials that black holes consume. For instance, as a black hole draws in surrounding gas and dust clouds, these materials reach incredible speeds and high temperatures. During this process, X-rays, a type of invisible light, are emitted from the disk of matter surrounding the black hole. It is through this light that we can detect active black holes. In 1971, during X-ray observations, this method proved successful, and an X-ray source named Cygnus X1 was discovered. This source appeared to be a blue supergiant star located about 6,000 light-years away from us. However, observations revealed that this star behaved quite strangely and was orbiting an unseen object. Interestingly, the object around which the star was orbiting had a mass of about 21 times that of the Sun. In the universe, the only object that could have such a massive mass without emitting any light was a black hole. Thus, Cygnus X1 was actually a binary system consisting of a black hole and a blue supergiant. The black hole here was pulling material from the surrounding star, causing X-ray bursts. Scientists made a groundbreaking discovery with this observation, as it marked the first time humanity had detected the presence of a black hole in space. This discovery did not halt the progress of scientists. On the contrary, it motivated astronomers to conduct more observations. Thanks to these observations, we learned that black holes are not only found in small sizes in the universe but also that supermassive black holes exist at the centers of galaxies, and some black holes are found in groups. For example, Sagittarius A*, the supermassive black hole at the center of the Milky Way galaxy, was one of the most significant examples of these discoveries. However, understanding what a black hole truly looks like required a much greater effort. In 2019, a groundbreaking event occurred in the scientific world. As part of the Event Horizon Telescope project, the first direct image of a black hole was captured using 8 different telescopes. The image you are seeing now is the first ever photograph taken directly of a black hole. Thus, the massive black hole at the center of the Messier 87 galaxy became visible to the human eye for the first time. In addition, although these formations may seem invincible from a distance, they are actually entities that succumb to time. This is because Stephen Hawking proposed that black holes could eventually evaporate by emitting radiation over time. According to this theory, known as Hawking radiation, black holes may not exist forever and could slowly evaporate and disappear at some point. While this theory may sound incredible, there are even more astonishing theories. For example, some theories suggest that black holes could be gateways to other universes. Some even propose that our universe might have been born inside a black hole. Before delving into these topics, we need to address a much more pressing issue: black holes that could be nearby and potentially pose a threat to us. So, where is the closest black hole to us located right now? Or, if a black hole were to enter our solar system, what would happen to us? To determine the locations of the nearest black holes to Earth, we first need to be able to detect them. However, since we are still in the early stages of understanding black holes, we don't yet have a definitive method for doing so. That said, there are a few ways we can detect them. One method involves observing the effects black holes have on their surroundings. Even an ordinary black hole has an incredibly strong gravitational pull, which can cause anomalies in space. For example, as a black hole passes through gas and dust clouds or travels among stars, it can tear material away from nearby celestial objects. If we can observe the X-rays emitted from this accretion disk, we can detect the black hole. Another way to discover black holes is through a phenomenon known as gravitational lensing. Black holes warp the fabric of space-time due to their immense gravity, which alters the path of light passing near them. If a black hole passes in front of a distant galaxy or star, it bends the light from that object, creating a lensing effect. This makes the distant object appear larger and brighter. By observing these subtle lensing events, we can identify the locations of rogue black holes wandering through space. Despite these detection methods, the number of black holes we have discovered so far is relatively small. However, mathematical models suggest that there could be as many as 100 million rogue black holes drifting through the Milky Way galaxy alone. So, why are these black holes wandering freely through the universe? There are three types of black holes in the universe: stellar mass black holes, intermediate mass black holes, and supermassive black holes. Stellar mass black holes form when the cores of massive stars collapse under their own gravity. Intermediate mass black holes are thought to form either through the merging of stellar mass black holes or the collapse of large star clusters. Supermassive black holes, on the other hand, are believed to have formed in the early universe from the collapse of population 3 stars or through the merging of smaller black holes and the accumulation of matter. All three types of black holes can become rogue black holes, drifting through the universe and potentially causing destruction in their paths. If a black hole were to enter our solar system, the consequences would be catastrophic. Its immense gravitational pull would disrupt the orbits of planets, comets, and asteroids, potentially flinging them out of the solar system or causing collisions. If Earth were to come close to a black hole, the tidal forces would stretch and compress our planet, leading to its eventual destruction. However, the likelihood of a black hole entering our solar system is extremely low, given the vast distances between celestial objects in space. For now, the closest known black hole to Earth is Gaia BH1, located about 1,560 light-years away. This black hole, discovered in 2022, is part of a binary system with a star. While it poses no immediate threat, its discovery highlights the importance of continuing to study these mysterious objects and improving our ability to detect them. As our understanding of black holes grows, so too does our ability to prepare for and mitigate any potential risks they might pose in the future. For a black hole to become a rogue black hole, strong gravitational interactions or collisions are sufficient. For example, if two black holes or a massive star come very close to each other, one can deliver a powerful gravitational kick to the other, potentially ejecting the black hole from its location into space. Similarly, when a galaxy merges with a larger galaxy, some black holes can be flung out of their positions due to intense gravitational forces, causing them to wander freely through the universe. Moreover, the number of such rogue black holes in the universe is not insignificant. In fact, we have managed to discover a few of them. One of these is the rogue black hole named OGLE 2011 BLG 0462, discovered in 2017 in the constellation Sagittarius. Located approximately 5,000 light-years away from us, this rogue black hole was detected using the microlensing method. It was observed for about 6 years, and its mass was estimated to be between 1.6 and 7.1 times that of our Sun. Additionally, it was found to be moving at a speed of about 45 kilometers per second. OGLE 2011 BLG 0462 is one of only 2 rogue black holes discovered so far. The reason we have detected so few is largely due to technological limitations, as our current telescope technology makes it extremely challenging to spot such black holes in real time. Another rogue black hole we have discovered is located in the galaxy 3C186 and was observed by the Hubble Space Telescope. However, this black hole is quite different. It is a supermassive black hole, located about 8 billion light-years away from us. Supermassive black holes are typically found at the centers of large galaxies and have masses at least 100,000 times that of our Sun. However, the supermassive black hole in 3C186 is not at the center of its galaxy. Instead, it is located about 35,000 light-years away from the galactic center. Observations show that the wavelengths of the X-rays emitted by this black hole are stretched, indicating that it is moving away from the center. In fact, current calculations suggest that this black hole is receding from the center at a speed of approximately 7.5 million kilometers per hour. So, what could cause such a massive and colossal black hole to be dislodged and turned into a rogue black hole? This scenario was likely the result of the collision and merger of 2 supermassive black holes, which generated powerful gravitational waves. Such collisions can eject black holes from the centers of galaxies, causing them to wander freely through the universe. This is yet another testament to the dynamic and violent nature of the cosmos. The discovery of rogue black holes highlights the complex and often chaotic interactions that occur in the universe. While they pose no immediate threat to us, their existence reminds us of the immense forces at play in the cosmos and the need to continue advancing our observational technologies to better understand these enigmatic objects. As we improve our ability to detect and study rogue black holes, we may uncover even more about the dramatic events that shape the universe. How do black holes form and why do they wander? Black holes in the universe come in 3 main types: stellar mass black holes, intermediate mass black holes, and supermassive black holes. Stellar mass black holes form when massive stars exhaust their nuclear fuel and collapse under their own gravity at the end of their life cycles. Intermediate mass black holes are thought to form either through the merging of stellar mass black holes or the collapse of dense star clusters. Supermassive black holes, which are typically found at the centers of galaxies, may have formed in the early universe through the accumulation of mass or the merging of smaller black holes. However, not all black holes remain stationary at the centers of galaxies. Some wander through the universe, and these are known as rogue black holes. Rogue black holes are often the result of dramatic cosmic events, such as the collision of 2 galaxies or the merging of 2 supermassive black holes. For example, the supermassive black hole in the galaxy 3C186 was likely ejected from its galactic center due to the gravitational waves generated during the merger of 2 galaxies. This black hole is now drifting through space at an incredible speed of about 7.5 million kilometers per hour. Are rogue black holes dangerous? Rogue black holes, while wandering through the universe, can indeed consume stars, planets, and other celestial objects in their path. However, the likelihood of a rogue black hole approaching Earth is extremely low. Astronomers estimate that there are about 100 million rogue black holes in the Milky Way galaxy alone, but most of them are located far from us. For instance, the closest known rogue black hole, OGLE 2011 BLG 0462, is approximately 5,000 light-years away from Earth. If a rogue black hole were to enter our solar system, it could disrupt the orbits of planets. However, this disruption would not necessarily lead to the destruction of planets. For example, if a black hole with a mass 6 times that of the Sun passed between the orbits of Mars and Jupiter, it could alter the planet's orbits. However, the probability of Earth being flung into space as a result of such an event is very low. The rarity of rogue black hole encounters. The vast distances between celestial objects in space make encounters with rogue black holes exceedingly rare. Additionally, the detection of these wandering black holes is challenging due to their nature. They do not emit light and can only be observed indirectly through their gravitational effects, such as microlensing or the distortion of light from background stars. While rogue black holes are fascinating and dramatic objects, they pose no immediate threat to Earth or our solar system. Their existence serves as a reminder of the dynamic and often violent processes that shape the universe. As our observational technologies improve, we may discover more about these enigmatic wanderers and their role in the cosmos. What lies inside a black hole? The question of what lies inside a black hole is one of the greatest mysteries in science. According to Einstein's theory of general relativity, at the center of a black hole lies a point called the singularity, where matter is compressed to infinite density, and the fabric of space-time breaks down completely. However, this idea conflicts with quantum mechanics, which states that nothing can have infinite density. This contradiction suggests that our current understanding of physics is incomplete, and a unified theory combining general relativity and quantum mechanics is needed to fully explain what happens inside a black hole. Some scientists propose that black holes might act as portals, potentially connecting distant regions of the universe or even leading to other universes. According to this theory, an object falling into a black hole could emerge in another universe or a different point in space-time. However, this idea remains speculative and has not been proven. What happens if you fall into a black hole? If you were to fall into a black hole, the experience would be both fascinating and terrifying. As you approach the event horizon, the boundary of the black hole, the gravitational pull becomes so strong that not even light can escape. Once you cross the event horizon, there is no turning back. As you are pulled toward the center of the black hole, you would undergo a process called spaghettification. This occurs because the gravitational force on your feet would be much stronger than on your head, stretching your body into a thin, spaghetti-like strand. After crossing the event horizon, you would eventually reach the singularity at the center of the black hole. At this point, we don't fully understand what happens. Some theories suggest that the fabric of space-time breaks down entirely, and the laws of physics as we know them cease to apply. Others propose that the singularity could be a gateway to another universe or a different point in space-time. The singularity, the heart of a black hole. At the center of every black hole lies the singularity, a point where matter is compressed to infinite density, and space-time is infinitely curved. The singularity can range in mass from a few times that of the Sun to billions of solar masses. All the matter and light absorbed by the black hole are thought to end up here, in a state where the laws of physics as we know them no longer apply. If a rogue black hole were to swallow Earth, and if we somehow survived crossing the event horizon, we would experience some bizarre phenomena. Inside the black hole, the singularity would no longer be a physical point in space but an inevitable event in our future. The space within the black hole would become so warped that all paths would lead inexorably toward the singularity. No matter which direction you moved, you would be drawn closer to the singularity. Additionally, time would become so distorted that you would perceive time outside the black hole as slowing down, eventually appearing to stop entirely. From your perspective, you would be frozen in time, forever falling toward the singularity without ever reaching it. This is because, inside the black hole, time itself stretches infinitely, making the journey to the singularity an eternal one. The paradox of the singularity. The singularity represents a point where our understanding of physics breaks down. It is a region where space and time cease to exist as we know them, and the laws of nature as we understand them no longer apply. While general relativity predicts the existence of singularities, it cannot fully describe what happens there. This paradox highlights the need for a new theory that unifies general relativity and quantum mechanics, often referred to as the theory of quantum gravity. The enigmatic nature of black holes and their singularities continues to challenge scientists and inspire new theories. Whether black holes are gateways to other universes, cosmic recycling centers, or simply regions of infinite density, they remain one of the most fascinating and mysterious phenomena in the universe. As we continue to explore and study them, we may one day unlock the secrets they hold and gain a deeper understanding of the cosmos. Wormholes, shortcuts through the universe. The extreme warping of space-time by black holes raises questions about their effects on the universe and the potential consequences. According to Einstein's theory of general relativity, black holes can bend space-time so drastically that they might create a theoretical passageway connecting distant regions of the universe. These hypothetical passages are known as wormholes. Wormholes are theoretical tunnels that connect different points in space-time, potentially allowing for rapid travel across vast cosmic distances. Just as a tunnel through a mountain can shorten the distance between 2 points, wormholes could create shortcuts through the fabric of the universe. In theory, we could use these shortcuts to travel to regions of space that are millions or even billions of light years away. Wormholes are not only an incredible possibility but are also consistent with the equations of general relativity. However, despite their theoretical existence, we have never observed a wormhole in reality. This has led some scientists to speculate that wormholes might not form through black holes but could instead exist as fleeting phenomena, appearing and disappearing in nanoseconds, possibly through mechanisms like cosmic strings. The challenges of wormholes. Even if wormholes exist within black holes, they would likely be impractical for travel. According to some solutions of general relativity, creating a wormhole would require 2 black holes, and such a wormhole would be incredibly unstable. The immense gravitational forces exerted by the black holes at either end of the wormhole would cause the passage to constantly stretch and contract, leading to its collapse within seconds of formation. Even if a wormhole could remain open for a longer period, it would still be far from a practical means of travel. Passing through a wormhole could result in being trapped in a temporal bottleneck, where time dilation effects might cause you to age rapidly or experience other fatal consequences. Additionally, some solutions of general relativity suggest that a single black hole might be sufficient to create a wormhole. However, such wormholes would also be unstable. The black hole forming the wormhole would continuously pull on it, causing the passage to stretch and contract, making it impossible to traverse safely. Are stable wormholes possible? At this point, scientists do not know whether stable wormholes exist in the universe. Some researchers speculate that unstable wormholes might only occur in ordinary black holes, those formed by the collapse of massive stars. However, the existence of stable wormholes remains purely theoretical. For a wormhole to be stable and traversable, it would require the presence of exotic matter, a hypothetical form of matter with negative energy density. Exotic matter could theoretically counteract the gravitational forces that cause wormholes to collapse, keeping them open long enough for travel. However, exotic matter has never been observed, and its existence remains speculative. Wormholes and the future of space travel. While wormholes capture the imagination as potential shortcuts through the universe, their practical use for space travel remains highly uncertain. The challenges of stability, the need for exotic matter, and the extreme conditions required for their formation make wormholes a fascinating but distant possibility. For now, wormholes remain a theoretical concept that pushes the boundaries of our understanding of space, time, and gravity. As we continue to explore the mysteries of black holes and the fabric of the universe, we may one day uncover whether these cosmic shortcuts are more than just science fiction. Until then, wormholes serve as a reminder of the incredible complexity and wonder of the cosmos. White holes, the opposite of black holes. White holes are, in their most basic sense, the opposite of black holes. If wormholes truly exist, there must be another exit for the light and matter that falls into a black hole. Scientists refer to this hypothetical exit as a white hole. But have we ever observed such a structure in the universe? Could there really be a white hole on the other side of a black hole? While a black hole pulls everything around it inward, a white hole repels everything that approaches it. Additionally, the event horizon of a black hole is a one-way boundary from which nothing can escape, whereas the event horizon of a white hole is a boundary that nothing can enter. If you tried to enter a white hole, you would be violently ejected back into space. However, this doesn't mean a white hole would repel all objects around it. If you could survive near a white hole for more than a few seconds, you would observe that it behaves similarly to a black hole in some ways. It rotates, has mass, and exerts gravitational pull. In fact, a white hole would initially attract surrounding objects due to its mass, just like a black hole. But as these objects approach the white hole's event horizon, they would be unable to proceed further. The appearance of white holes. This behavior suggests that white holes might not be the bright, dazzling objects we imagine them to be. In fact, from a distance, a white hole might resemble a black hole due to the presence of an accretion disk around it. The key difference between a white hole and a black hole is that a white hole does not consume matter and energy. Instead, it expels them outward into space. However, this expulsion of matter likely doesn't last for very long. If a white hole continuously ejected large amounts of matter, it would eventually undergo gravitational collapse and transform into a black hole. For this reason, scientists believe that the matter ejection from a white hole must be rare and short-lived. Do white holes exist? Despite their theoretical consistency with the equations of general relativity, white holes have never been observed in the universe. Some scientists speculate that white holes could be the other end of wormholes, providing an exit for matter and energy that falls into a black hole. However, this remains purely speculative, as no evidence for white holes or wormholes has been found. Another possibility is that white holes could be connected to the Big Bang. Some theories suggest that the Big Bang itself could have been a white hole, expelling matter and energy into the universe. However, this idea is still highly speculative and lacks empirical support. The challenges of white holes. One of the biggest challenges in studying white holes is their instability. According to general relativity, white holes are highly unstable and would likely collapse into black holes almost immediately after forming. This makes their existence in the universe unlikely, at least in a long-lasting form. Additionally, the conditions required for a white hole to form are extreme and have never been observed in nature. While they are fascinating theoretical constructs, white holes remain one of the most elusive and mysterious concepts in modern physics. White holes and the future of physics. White holes challenge our understanding of space, time, and gravity. While they may not exist in the universe as we know it, they serve as a valuable tool for exploring the limits of general relativity and the nature of singularities. As we continue to study black holes, wormholes, and the fabric of the universe, we may one day uncover whether white holes are more than just a theoretical curiosity. For now, white holes remain a fascinating what-if in the realm of astrophysics, reminding us of the endless possibilities and mysteries that the universe holds. The existence of white holes and thermodynamics. In essence, we are searching for something in the universe that might exist for only a few seconds and can only be distinguished by a brief, explosive event, something resembling a black hole but behaving in the opposite way. So far, we have not observed anything like this in our observations. We don't know whether we haven't seen them because they don't exist or because they are extremely rare. The only thing we know for sure is that, according to the theory of general relativity, white holes could theoretically exist in the universe. However, while general relativity allows for the possibility of white holes, their existence is fundamentally at odds with the laws of thermodynamics. White holes tend to decrease entropy, which violates the second law of thermodynamics. Entropy, a measure of disorder, dictates that everything in the universe moves from order to chaos over time. For example, living organisms age, objects wear down, and stars explode at the end of their lives. In short, entropy is the direction of time's flow, and as time progresses, disorder, entropy, continuously increases. This law makes the existence of white holes impossible because they appear to reduce disorder, effectively suggesting that time could flow backward, a phenomenon that defies the fundamental principles of physics. White holes, a mathematical concept. White holes are purely mathematical constructs. While they are mathematically possible within the framework of general relativity, there is no physical evidence to suggest they exist. No known physical process can create a white hole, and no observational data has ever hinted at their existence. In fact, not only have we never observed a white hole, but we also haven't found any trace of one. Black holes and other universes. Another intriguing possibility related to black holes is the idea that they might serve as gateways to other universes. If you were to fall into a black hole, you might emerge in a completely different universe. Some scientists have drawn parallels between the singularity of a black hole and the Big Bang, suggesting that the Big Bang itself could have occurred inside a black hole. According to this theory, the wormholes that might exist inside black holes could lead not to a white hole or another location in our universe, but to an entirely new universe. In this scenario, beyond the event horizon of a black hole, a new space-time fabric could form, giving rise to the birth of a new universe. This idea suggests that black holes might not just be cosmic vacuum cleaners but also cosmic creators, potentially spawning entirely new universes within their depths. The challenges of these theories. While these ideas are fascinating, they remain highly speculative. The concept of white holes and black holes as gateways to other universes pushes the boundaries of our current understanding of physics. Both ideas rely on extreme conditions and hypothetical phenomena that have not been observed or proven. For example, white holes violate the second law of thermodynamics, making their existence unlikely. Black holes as gateways require the existence of stable wormholes and exotic matter, neither of which has been observed. The future of exploration. Despite the challenges, these theories inspire scientists to explore the limits of our understanding. They remind us that the universe is full of mysteries waiting to be uncovered. As we continue to study black holes, wormholes, and the fabric of space-time, we may one day find answers to these profound questions. For now, white holes and the idea of black holes as gateways to other universes remain captivating thought experiments that challenge our imagination and push the boundaries of science. They serve as a reminder that the universe is far stranger and more complex than we can currently comprehend. The proliferation of universes and cosmological natural selection. Could every black hole in our universe actually be creating a new universe? And could our own universe have been born from a black hole in a larger, parent universe? While the idea that a black hole could give rise to an entire universe might sound far-fetched, it is one of the most compelling explanations for the origin of our universe and the nature of existence. According to the classical Big Bang theory, our universe began as an infinitely dense point of zero volume and has been expanding ever since, eventually forming planets, stars, and galaxies. However, the Big Bang theory leaves some critical questions unanswered. For example, what caused the Big Bang? What is the source of dark energy, which is accelerating the expansion of the universe? How did the physical laws of our universe come into existence? To address these questions, some theoretical physicists have proposed a theory called cosmological natural selection. This theory suggests that our universe is not the only one in existence. Instead, there are countless universes of various sizes, and each time a black hole forms in one of these universes, a new universe is born inside it. In other words, universes proliferate through the formation of black holes, and our own universe may have originated from a black hole in another, larger universe. How does cosmological natural selection work? To better understand this theory, we can draw an analogy from the process of natural selection in biology. In nature, the traits of living organisms evolve and diversify through natural selection, which favors individuals better adapted to their environment. For example, consider two populations of rabbits living in a snowy forest, one with white fur and one with brown fur. The white rabbits blend into the snowy environment, making them less visible to predators, while the brown rabbits stand out and are more likely to be hunted. Over time, the white rabbits survive and pass on their genes, while the brown rabbits may eventually disappear. Additionally, the surviving white rabbits may develop slight variations, such as larger ears or thicker fur, further adapting to their environment. Similarly, cosmological natural selection suggests that universes evolve through a process akin to biological natural selection. Universes that produce more black holes are more likely to reproduce by giving rise to new universes. Each new universe inherits some properties from its parent universe but may also develop slight variations in its physical laws. Over time, universes that are better at producing black holes become more common, just as white rabbits become more common in a snowy forest. Black holes as cosmic reproductors. In this framework, black holes serve as the mechanism for the reproduction of universes. When a black hole forms, it creates a new universe inside it, complete with its own set of physical laws. These new universes may have slightly different constants of nature, such as the strength of gravity or the speed of light, compared to their parent universes. Over countless generations, universes that are more efficient at producing black holes become dominant, while those that are less efficient fade away. This theory provides a compelling explanation for the origin of the Big Bang and the fine-tuning of the physical laws in our universe. According to cosmological natural selection, the Big Bang was not a singular event but rather the birth of a new universe inside a black hole. The physical laws of our universe are the result of a long process of cosmic evolution, shaped by the need to produce black holes efficiently. Implications of cosmological natural selection. If cosmological natural selection is correct, it has profound implications for our understanding of the universe. 1. Multiverse. Our universe is just one of countless universes, each with its own unique properties. 2. Fine-tuning. The physical constants of our universe are not arbitrary but have been shaped by a process of cosmic evolution. 3. Black holes as cosmic seeds. Black holes are not just destructive forces but also creative ones, serving as the seeds for new universes. Challenges and criticisms. While cosmological natural selection is an intriguing theory, it is not without its challenges. Observational evidence. There is currently no direct evidence for the existence of other universes or the idea that black holes create new universes. Mathematical complexity. The theory relies on complex mathematical models that are difficult to test or verify. Alternative explanations. Other theories, such as string theory and the multiverse hypothesis, offer different explanations for the origin of the universe. The future of cosmological natural selection. Despite these challenges, cosmological natural selection remains a fascinating and thought-provoking theory. It bridges the gap between cosmology and evolutionary biology, offering a new perspective on the origin and evolution of universes. As our understanding of black holes, quantum gravity, and the early universe continues to grow, we may one day find evidence to support or refute this theory. For now, cosmological natural selection serves as a reminder that the universe is full of mysteries waiting to be uncovered. It challenges us to think beyond the boundaries of our own universe and consider the possibility that we are part of a much larger, ever-evolving cosmic ecosystem. Black holes and the formation of universes. For a universe to create black holes, it needs stars. Universes that produce more stars may become more conducive to the emergence of life, much like our own universe. The more stars a universe has, the more planets it can form, increasing the likelihood of life arising. Thus, this theory also provides an answer to the question of why life exists in our universe. But is this seemingly perfect idea actually plausible? And, more importantly, is it testable? To prove this idea, we would need to demonstrate that black holes truly give rise to new universes. This is one of the theory's greatest challenges because we know very little about what happens inside black holes. That said, we do know that black holes share some similarities with the state of the universe before the Big Bang. For instance, when a black hole forms, its immense gravitational pull compresses everything toward its center. Atoms are torn apart, temperatures exceed 100 billion degrees, and all matter is squeezed into an infinitely small point. If we use Einstein's theory of general relativity to understand what lies at the center of a black hole, we arrive at a singularity, a point of infinite density. Interestingly, the Big Bang also began from a state resembling a singularity. According to this theory, the singularity at the center of a black hole undergoes a quantum mechanical bounce, causing it to suddenly expand. However, because this expansion cannot fully escape the black hole's gravitational pull, it creates a new space-time structure on the other side of the black hole. This process closely resembles the Big Bang. While this idea sounds logical, proving it would require us to peer inside a black hole, a feat that is currently impossible. Classical black holes do not allow any information to escape, making it extremely difficult to test this theory directly. As a result, determining whether a black hole contains another universe remains beyond our current capabilities. Black holes, cosmic giants or building blocks of a larger structure? As you can see, black holes are one of the greatest mysteries of the universe. At this point, we don't know whether they are merely cosmic giants that devour matter or fundamental building blocks of a much larger structure. Some theories, such as string theory, even suggest that black holes could contain parallel universes. The only way to resolve these questions is through further research. Advances in telescope technology, quantum physics, and gravitational wave studies are bringing us closer to unraveling the secrets of these cosmic giants. Perhaps one day, we will understand what black holes truly are and solve one of the universe's greatest mysteries. For now, the only thing we know for certain is that something extraordinary lies within black holes. These immense gravitational wells are among the most enigmatic phenomena in the universe, and one day, we may finally uncover their secrets. The role of black holes in cosmic evolution. Black holes play a crucial role in the evolution of galaxies and the universe as a whole. They influence the formation of stars, the distribution of matter, and even the structure of space-time. Some scientists believe that black holes could be the key to understanding the origins of the universe itself. For example, galactic centers, supermassive black holes, found at the centers of galaxies, regulate star formation and galactic evolution. Gravitational waves, the collision of black holes produces ripples in space-time, known as gravitational waves, which provide insights into the nature of gravity and the universe. Cosmic recycling, black holes may recycle matter and energy, contributing to the formation of new stars and galaxies. The future of black hole research. The study of black holes is a rapidly evolving field, with new discoveries being made regularly. Projects like the Event Horizon Telescope, which captured the first image of a black hole in 2019, and missions like LISA, Laser Interferometer Space Antenna, which will detect gravitational waves from space, are pushing the boundaries of our knowledge. As we continue to explore these cosmic enigmas, we may uncover answers to some of the most profound questions in science. What lies inside a black hole? Do black holes create new universes? How do black holes shape the evolution of the cosmos? For now, black holes remain one of the most fascinating and mysterious phenomena in the universe. They challenge our understanding of physics, space, and time, and inspire us to keep exploring the unknown. One day, we may finally unlock their secrets and gain a deeper understanding of the universe we inhabit.